Welcome to Math 22 discussion video on trigonometric integrals. Now don't forget to watch the lecture video before watching this discussion video because there are so many cases of trigonometric integrals and we will be diving into exercises right away, and I will be referring to the cases in the lecture video. So let's go to the exercises. Now, these will be the integrals that I will be discussing in this video. If you want, you can take a screenshot first. Notice that these integrals are all of different cases. By cases, I mean the cases discussed in the lecture video. And as per in the lecture video, for most of these cases, you will split off a factor of any of the derivatives of the 6 trigonometric functions. So, split off maybe a cosine x, a sine x, a secant squared x, etc. Anyway, without further ado, since there are many cases, let us just dive into the examples. Integral of sine to the 7th of x dx. So what case is this? This is the case where you have the integral of an odd power of sine x. So what do we do? What we will do is, we will split off a factor of sine x as stated in the lecture video. So let's do that now. So integral of sine to the 7th of x dx is equal to integral of sine to the 6th of x times sine x dx. Now we will use sine x dx to be our du. So we need a cosine x in the integral here. But no problem, because sine to the 6th of x is an even power of sine. It is the same as sine squared x cubed. So, using the Pythagorean identity, we will write sine to the 6th of x as 1 minus cosine squared x cubed. So, our integral now is integral of 1 minus cosine squared x cubed times sine x dx. And as I've said a while ago, our u will be cosine x because our du is sine x dx. But this time, there's a negative sign. But that's not a problem. We will just move the negative sign to the other side. So sine x dx here becomes negative du. And let us apply the substitution. So by substitution, our cosine squared x here becomes u squared. And our sine x dx becomes negative du. So the negative sign goes outside. So our integral is integral of the quantity 1 minus u squared cube du. And then let's expand what is 1 minus x squared cube. This is just a polynomial. Using the perfect cube formula, or by expanding on your own, you will see that 1 minus u squared cube is 1 minus 3u squared plus 3u to the 4th minus u to the 6th. Notice that this integral is just the integral of a polynomial which can readily be integrated by the power rule. So the integral is negative times the quantity u minus u cube plus 3/5 u to the 5th minus 1 over 7 u to the 7th plus c. And don't forget from Math 21, the final step is to bring back the function in terms of x. So we will be substituting u equals cosine x back into this expression. So finally, our integral is negative cosine x plus cosine cube x minus 3 cosine to the 5th of x over 5 plus cosine to the 7th of x over 7 plus c. I just distributed the minus sign. That's why there's no more parentheses here. And that's it. So in this case, integral of an odd power of sine, we will split off a factor of sine x dx and let u be cosine x and express the remaining power of sine as cosine. So let's pause a bit before going to the next problem. Okay, let's go to the next problem. Integral from 0 to 1 of sine squared of pi x times cosine squared of pi x dx. Now notice that this is the case where you have a product of even power of sine and an even power of cosine. So what do we do here? Well, for even power of sine and even power of cosine, we will use the half angle identities. So just recall half angle identities from the Math 20 videos. Anyway, our integral now becomes integral from 0 to 1 of, by half angle identity, sine squared pi over x is 1 minus cosine of 2 pi x all over 2. And cosine squared pi x is 1 plus cosine of 2 pi x all over 2. Now, first things first, let us expand this product and move the 1/4 outside. So the integral becomes 1/4 integral from 0 to 1 of the product of the numerators. And notice that the product of the numerators is just a difference of two squares. So I'll write it down here as 1/4 integral from 0 to 1 of 1 minus cosine squared 2 pi x dx. Now, by the Pythagorean identity, this is equal to 1/4 integral from 0 to 1 of sine squared 2 pi x dx. Now, how do we integrate this? This is an integral of an even power of sine. So, of course, use half angle again. So, by half angle, sine squared 2 pi x is equal to 1/4 integral from 0 to 1 of 1 minus cosine of 4 pi x all over 2 dx, and I will just put the 1/2 outside to get 1/8 integral from 0 to 1 of 1 minus cosine 4 pi x dx. Now notice that we can now directly integrate this. And of course, the integral is equal to 1/8 times the quantity x minus 1 over 4 pi sine of the quantity 4 pi x. And then we will substitute 1 minus substitute 0 as per the rules for the definite integral. And so we will have this expression, and evaluating that just gives 1/8. And that's it. Let's pause for a bit before going to the next problem. Integral of cotangent to the fifth of x dx. Now notice that this case is the integral of an odd power of cotangent or tangent. So what do we do here? Well, what we will do here is we'll split off a factor of cotangent squared. So let's do that now. So cotangent to the fifth of x dx is equal to cotangent cube of x times cotangent squared dx. And as per in the lecture video, we will express the cotangent squared x as cosecant squared x minus 1. And we'll do so here. Now let us distribute the cotangent cube x over the cosecant squared x minus 1 and split the integral. So we will get cotangent cube of x cosecant squared of x dx minus integral of cotangent cube of x dx. So notice that the first integral can readily be evaluated by a substitution, since the derivative of cotangent x is negative cosecant squared x dx, and this is just cotangent of x and then cube. For the second integral, we go back to the same case as the original integral. So we will have to split off a factor of cotangent squared and then write that cotangent squared as cosecant squared x minus 1 again. So that's what I'm gonna do here. And let us again perform the same steps. So distribute the cotangent x over the product and split the integral. So our integral now is integral of cotangent cube x cosecant squared x dx minus integral of cotangent x cosecant squared x dx plus the integral of cotangent x dx. Let us just evaluate integral of cotangent x dx, which is ln of absolute value of sine x. This is just from the formula. And then let's combine these first two integrals. So we will get integral of cotangent cube minus cotangent x and then cosecant squared x dx. Why did I do this? So that it's easier to just apply the substitution. So the substitution here will still be u equals cotangent x, because our du is negative cosecant squared x dx, which is right here. So let's do that now. So let u be cotangent x. So du is negative cosecant squared x dx. And let's apply the substitution to this integral here. So the integral becomes our original integral, cotangent to the fifth of x dx is equal to cotangent cube x becomes u cube and then minus u times cosecant squared x dx is negative du. And then plus ln of absolute value of sine x. And then let's just put the negative sign here on the du outside. So this gives us negative integral of the quantity u cubed minus u du plus ln of absolute value of sine x. And notice u cubed minus u is just polynomial. We can evaluate that directly. So the integral is negative quantity 1/4 u to the fourth minus 1/2 u squared. And then the rest of the expression, so plus ln of absolute value of sine x plus c. And finally, what's our final step? We will substitute back u equals cotangent x. So we get negative 1/4 cotangent to the fourth of x plus 1/2 cotangent squared of x plus ln absolute value of sine x plus c. Notice that I just distributed the minus sign. And that's it. So let's pause a bit before going to the next problem. Integral of secant to the fourth of x dx. Notice that this is the case where the integral is the integral of an even power of secant or cosecant. So by the lecture video, what do we do here? What we will do is we will split off a factor of secant squared of x. So let's do that. So secant to the fourth of x dx integral is equal to secant squared x dx integral, and we want our du to be secant squared x dx. So we will have to find a tangent somewhere. But fortunately, secant squared x is 1 plus tangent squared x. So let's write it as such. So we will get integral of the quantity 1 plus tangent squared x times secant squared x dx. And so we will have, by splitting the integral of secant squared x dx plus the integral of tangent squared x secant squared x dx. And notice that the first integral can be evaluated directly. So you'll get tangent x, and then let's copy the second integral. So as I've said a while ago, we want u to be tangent x, so that du will be secant squared x dx. And let's apply this substitution now to the second integral, or the integral that's left. So using the substitution, our integral here, the integral of tangent squared x secant squared x dx, becomes integral of u squared du. And this is just a polynomial, so we can directly integrate this. So our original integral of secant to the fourth x dx, is equal to tangent x plus 1/3 u cubed plus c. And what's the final step? Final step is to substitute back into x. So we will get tangent x plus 1/3 tangent cube of x plus c. And let's pause a bit before going to the next problem.